Hi everyone, in this episode we're going to take a look at a concept that makes Rust different from almost every other language, so it's worth your full attention. It's called ownership, and it's how Rust manages memory. Now most languages pick one of two approaches. Some use a garbage collector, which is a background process that periodically finds and frees the memory that you're no longer using. Convenient, but it does cost performance and predictability. Others, like C, make you free memory by hand. Fast, but it's easy to get it quite wrong. Rust takes a third path. It uses a set of rules checked by the compiler before your program ever runs. And this frees memory automatically at exactly the right moment, with no garbage collector and no need to manually free it. It takes a little time to click, so we're going to go slowly, and everything later in the series will build on top of it. Now we will take a look at the difference between the stack and the heap, the three rules of ownership, what a move is and why a moved value cannot be used again, and when values are copied instead of moved, and how ownership travels in and out of functions. But let's take a look at this diagram here. So to understand ownership, you need a simple mental model of two regions of memory, the stack and the heap. So the stack is fast and strictly orderly. Picture a stack of plates. So you add to the top and remove from the top, and everything has a known fixed size. Values whose size is known ahead of time live here. So this is an integer, a boolean, a single character. Pushing and popping the stack is almost free. Now the heap is for data whose size can grow or is not known in advance. So picture a large open floor where you can ask for a chunk of space and get back the address of that chunk. It's a more flexible, but it is slower, because the program has to find the space and later give it back. When you create a growable string, the actual text lives on the heap. And on the stack, you keep a small bookkeeping value with three parts: a pointer to the heap data, the current length, and the capacity. Hold on to this model because ownership is really just a set of rules about who is responsible for cleaning up the heap data. Now there are three rules of ownership. The first one is each value has a single owner, the variable responsible for it. Secondly, there can only be one owner at a time. And finally, when the owner goes out of scope, the value is dropped and its memory is freed automatically. That word scope means the region of code where a variable is valid, usually the block of curly braces that it lives in. When execution reaches the closing brace, the owner goes away, and Rust runs the cleanup for its value right there. The third rule is the heart of it. You never write the freeing of memory yourself, and you can never forget to, because the compiler inserts the cleanup for you at the end of the scope. Everything else about ownership follows from keeping these three rules true. So let's see what actually happens when we assign one heap value to another. Let me open up the Explorer and open up this main.rs file. And let's write the following. Get a little bit more real estate, and I'll open up a terminal. Just clear that. We're in the ownership folder, so let's go ahead, cargo run, and that should print hello. So this is a pretty basic program. It works and it's printing hello as we can see, but something more subtle is happening on this middle line here. You might expect S1 and S2 to both be valid now, which is two names for the same text, but that's not what's happening. When we wrote this let S2 equal S1, ownership of the string moved out of our S1 variable and into S2, and S1 became invalid. Let's prove that by trying to use S1 as well. So I'll copy and paste this and change that to S1. And let me try and run that again. So we've got an error this time. Let's read the error closely and slowly, because reading errors calmly is one of the most useful skills you can have, whether you're programming in Rust or any language. Essentially, what this error message is telling us is that the value was moved and points at exactly where it happened, which is where we tried to use the s1 variable. Why is Rust so strict like this? Well, if both s1 and s2 believed they owned the same heap data, both would try to free it at the end of the scope, and freeing the same memory twice is a classic but dangerous bug. The move rule that Rust imposes makes this mistake impossible. So let's go ahead and just delete this extra line. And if we try and compile it again, we'll see that we're back to printing hello with no bugs reported. What if you genuinely want two independent copies of the heap data? You can ask for it on purpose using clone. Let's get out of our terminal and let's see this in action. Alright, so let's run this. I'll just clear that up. Go cargo run. Okay, so both S1 and S2 are valid here because clone made a full separate copy of the text on the heap. The word clone is deliberately visible in the code, and it tells you what the real work is doing, a heap allocation and a copy, so it never surprises you. Integers behave a little differently. I'll just get a little bit more real estate here. I'll see both lines of code. There we go. X is still usable after let y equals x, even though we never cloned. That is because small, fixed-size stack values are so cheap to copy that Rust just copies them and leaves the original valid. Types that behave this way implement a built-in trait called copy. You may remember copy if you followed along with the rock and paper scissors project that we built earlier. Integers, booleans, characters, and floats can copy. Strings cannot, because duplicating heap data is not free, which is exactly why a string moves instead of copying. Now let's take a look at ownership and functions. So passing a value to a function follows exactly the same move rule as assigning it. Here it's in both directions at once, so a function that takes ownership and one that gives it back. So let's actually go ahead and write that code. Alright, so now let's run this. Okay, so when we pass s into takes ownership, as we're doing here, ownership moves into the function, so s is no longer valid back in main. When that function ends here, the parameter goes out of scope and the string is dropped right here. Returning a value moves ownership the other way, out of the function and to whoever called it, which is how got ends up owning yours. If this constant handling of ownership in and out of functions sound tedious, you're right, and you've spotted the exact problem that references solve. Most of the time, you don't want to give a function ownership of your value. You just want to lend it for the moment that the function's going to use it. That's what references are for, and that's the whole subject of our next episode. Before we move on to references, make sure you know the following. So make sure you can state the 3 ownership rules in Rust from memory. If you need to refresh yourself, go back to the start of this video where we talked about that. When you're working with Rust code, try to predict whether a given assignment moves or copies. So get your hands dirty with Rust and really try to understand how ownership works within your Rust programs. And then when you run into compiler errors, make sure you're able to explain what that error is that occurs from moving a used value. Now, the code for this course will be available on my GitHub account. I'll post a link to this particular code in the description below, along with some other resources. If you like this video, give it a like. If you want to catch more videos on Rust, you're following along with the series, make sure that you're subscribed so you don't miss out. If you have any questions, please pop them in the comment section below. And we'll see you all in the next video.